Okay, welcome to section number 7. A couple announcements before we start. First of all, the QR code, so if you want to do a scan. I'm actually excited for the responses today. It's one of my favorite questions, which is, what was one of your favorite classes that you took in college, or if you're a high school student in high school? I'm always curious what people's answers are. Tonight, regrade requests are due for exam 1. Also, the quiz for lecture 7 is due. There are a couple announcements that are kind of more me things for next week that y'all should be aware of. So every year during week 5, I hold mid-semester check-in meetings. And essentially what I'm doing is I'm setting aside like 9 or 10 hours next week to meet with students. And I really want to meet with like everyone. What will happen is I will send out emails with signups to like a little Calendly where you can sign up for a slot. And they will be 10-minute meeting slots. So it will be a very targeted check-in of like, come to the meeting with, hi, I'd like to discuss this thing. I'd like to discuss this part of the exam, or I'd like to discuss the way I'm currently studying for reactions and get some feedback on how I'm studying with it. You can come in and be like, hey, I never learned chairs. Can you teach me chairs? Sure. But just because it's 10 minutes, it will be pretty much like straight, direct to the point. It can also just be like, hey, I'm doing okay. Like my grade, I would love it to be higher, but like I also know what I'm doing and I'm studying and everything's fine. So it does not need to be like you're coming with an acute issue. It really just is a check-in. And then if you are a student that needs more time, like if you have more things that you wanted to talk through, or especially if the first exam was a little bit rougher than expected, feel free to sign up for like 2 slots. Just kind of be aware that everyone's going to be signing up for slots and there was only one me. The other thing is mid-semester feedback. So normally in week 5, we also send out a mid-semester kind of feedback survey that's anonymous on Canvas. And it's essentially just asking you about things that are working and not working in the course, just so we can kind of hear from you before the class is done. I know that it's already like more than halfway, and so I think that you're in it, and this is when you'll be able to kind of provide the best feedback as to how it's going. But we typically provide some sort of reward for if like 80 or 90% of the class like does the survey. I haven't talked with Tim about the exact logistics, but in the past I think we've like added 3% to everyone's exam score of some sort. And so I don't know what the exact reward will be, but like we value feedback, we read all of it, we read your responses. So that's there. Any questions, kind of logistic things for the next several days or the next week? Okay. Work. Oh, yeah. That was just your hand. Okay. So, full disclosure, lecture 7's my least favorite lecture. I just don't feel like it has a good story. Like, substitution elimination, like everything was building to the GFP system and it was like very like coherent of an idea, whereas like lecture 7's more hodgepodgey. You have like carbocations do funky things and alcohols leaving and ethers and epoxides, where it just feels a little bit more kind of disjointed. The connection is like, if I had to give this lecture a title, it would be like intricacies with substitution and elimination. Because most of these reactions that you are learning are based on like SN1 or SN2, but they're with some specific functional groups now, or we're introducing the rearrangement kind of idea. But again, not my favorite. I also don't think it's particularly hard. Like, I think that the challenge of it is just finding a way to organize it internally. And so I do want to touch on each of these, but I only want this to be about 50 minutes of section. And then I want the last 40 minutes to be these last 3 topics. So, do y'all remember my TED Talk from section 3 of like how to study reactions? So it's a trilogy. Today we will be doing part 2. Next Friday we will be doing part 3. And so I will talk through kind of a method for studying reactions I really like that I think is pretty effective. Then we're going to go through one of the hardest synthesis on the problem set, and it's probably the hardest synthesis you'll have seen so far. And we're going to work it together for like 15 to 20 minutes. And then I have an extra challenge problem that is going to be almost identical to like what the first page of exam 2 is going to look like. And it's going to be substitution elimination stuff. So I really want to kind of make time for this like content review. That means that this lecture 7 stuff, I'm going to be pretty quick on. I do want to like answer questions and want to make sure it's covered. But again, I don't think any of these reactions you're going to be like scratching your head at. Like, I think it's more so just going to be like, oh, I do SN2 in this circumstance, I do SN1 in this circumstance. Logistical questions or any questions before we jump in? I've also done something unhinged, and I hope that y'all won't judge me too much for it. So did I ask y'all about ideas for like transitions between the sections, or the topics? So I did get 30 audio clips, and I have a soundboard of transitions lined up. So let's try a transition and see how it goes. Carbocations. They do funky things. So one thing to remember from lecture 6 is that the more substituted a carbocation is, the more stable it is. So here a tertiary carbocation is the most stable of all these. What would be a carbocation that would be even more stable than tertiary? Something that's stabilized by resonance. So you're right, like something with an alkene, and something that has resonance here. That's going to be even more stable than hyperconjugation. And the big idea with carbocation rearrangements is if you can form a more stable molecule, you will. So let's look at the two kind of main examples that we introduced of the hydride shift and the methyl shift. So here, what type of carbocation do we have? Secondary. And then what type of carbon is this? Tertiary. I know the answer is right here, but do the thinking. So when we have a secondary carbocation next to a tertiary carbon, what's going to happen is this sigma CH bond is going to just scooch over. And we call it a hydride shift. And specifically, it's a hydride shift because the hydrogen with its electrons is all moving over to the right. And when that moves over, taking its electrons, we now have added a hydrogen there. There was one initially, so maybe I'll just draw it so that you see it. And then we've robbed that other carbon, the tertiary one, of a hydrogen, so it has the positive charge now. So now we're left with a tertiary carbocation. Is that more stable? Great. So it's the idea that if we can form the more stable cation, we will. And here it's going from secondary to tertiary. Similarly, if we have a secondary carbocation next to a, what type of carbon is this? Quaternary, because it's attached to 1, 2, 3, 4 carbons. So if we have it next to a quaternary carbon, then a methyl group with its electrons can shift over. And for both of these, be very careful that your arrow starts at the bond. So when that moves over, yet again, we create a tertiary carbocation, which is more stable. So this is the whole idea of like, you're walking around Harvard Square. You're not just going to walk into the road without looking both ways before crossing, right? Because otherwise, that's a recipe to become roadkill. So similarly, when you have a carbocation, you need to look both ways before proceeding with the reaction. You need to check and make sure that there is not a more stable rearrangement that we could do to make a more stable carbocation. Because otherwise, you will be in this situation. I'm confident. I'm doing my mechanism. I can make a carbocation. Oops. Whoops. I also didn't show with the mid-semester meetings. You get a meeting, and you get a meeting. You all get meetings. And this is very valid organic chemistry feedback. No. But honestly, I know that there are some students who want to say this, and I appreciate the restraint of those students. Okay, so those are the rearrangements. I didn't have time to bring up the sound cue, but I do have stranger rearrangements. So these are the basic ones that we teach you in lecture. And there are many other rearrangements that can happen that can get really crazy. Like I've seen some rearrangements where an atom is simply hopping over like 6 other atoms. And it's a 1-7 rearrangement, sigmatropic. Crazy. Y'all aren't gonna do that much, but y'all are gonna do some weirder things. And so I wanted to touch on these like few moments in the problem set where you see kind of more complicated rearrangements. So let's start off with this reaction with HBr and an alkene. I'm not gonna do, after this, any other reactions with alkenes today, because that is the sole focus of lecture 8. So I do all of alkenes for section 8. But in this reaction, the alkene's going to go and grab a hydrogen from HBr. And then we have two options. So option one is we add the hydrogen over here and we create this carbocation. Option two is we add the hydrogen here and create this carbocation. Which are we going to do, option one or two? Which carbocation is more stable, the one in one or two? This one, because this is a secondary carbocation, right? And this carbocation is primary. So the basic principle is we are going to form the more stable molecule each time when we have a choice. So we are going to go with option one over here. Oh yeah, sorry, this is connected to more carbons, so maybe that's why that, like it's this essentially. Like carbocation here, that's a single bond and a hydrogen. Yeah. So let's draw what that looks like. Here. So we have a secondary carbocation, and what type of carbon is it connected to over here? Quaternary. So what would we expect to happen if we have a secondary carbocation next to a quaternary carbon? Methyl shift. Draw it. So our methyl has moved over, and now our carbocation is where the methyl left. And so this is a tertiary carbocation. It's more stable, right? Okay. Well then from here, the Br minus can finish the reaction and attack, and then we get this product. Now this is fine and dandy, and it works. But if we wanted to, hypothetically, make the product that looks like this, where we added the bromine right where that first carbocation was, we're not going to get that. Just because this carbocation will shift so quickly to form something more stable. So I'm going to draw a little red arrow, or red X over it, of like, we actually don't get that product. So based on what we've told you, this is 100% what you would be expected to do initially. But there's another option. So, we talked in the past about how rings have strain, right? Like here, the angle in this cyclobutane is 90 degrees. It wants to be 180 degrees. And 5-membered rings are pretty stable, but 6 is really where it's at. Like 6 is the most stable ring size that you can get. And so if you have a carbocation and you have the option to do some sort of rearrangement that would expand your ring, that is actually going to be preferred. So let me show you. So down here, if instead of having the methyl group move over, if we have this sigma bond here move over, then we should get a bigger ring. But that's going to be a little tricky to draw. So I'm going to use my tool of numbering again, because that's really, really helpful for these types of problems. So I'm going to label the carbocation 1, and then 2, 3, 4, 5, 6. And essentially with this rearrangement, I'm going from a 2-6 bond to now 1 and 6 going to be bonded. 2-6 becomes a 1-6 bond. So we would call this on the arrow a like 1-2 alkyl shift. And then to draw our product, I know I made a 6-membered ring because I've connected 1 and 6. So I'm just going to draw the hexagon, and then I'm going to put my numbers, and that's going to help me finish off the structure. So on carbon 1 over here, what else do I need other than the other carbons that are labeled in red? What else is it attached to over here? A methyl. So I need to make sure that that's on 1 over here. Then carbon 2, what else does it have attached to it? A methyl. And those are the only dangly bits. Where is our carbocation now? who did we rob of a bond? So, but which of those between 2 and 6? Because I heard competing things. 6 went from being bonded to 2 to now 6 is bonded to 1. So it just swapped out a bond. It has the same things. Like here, we can see maybe if we draw the hydrogens, there are 2 hydrogens there. She still has 2 hydrogens, so she's good. 2 is who we've robbed. 2 was in the relationship with 6, and then 6 just up and left. So, we would have this carbocation now. Wild. A little bit different than what we've taught you, but do you see how this is kind of conceptually connected of we're forming a more stable molecule by doing a rearrangement? Work. So then at this point the Br minus could come and attack, and we could get this product. And this bottom one is going to be our major product, but this top one is the one that we would expect you to do kind of first. And so both of these are valid, both of these are probably happening, but I think this would be the major product. It doesn't look like which one? This or this? It doesn't look like this. Yeah, because this one's more stable. This is the better product to form. Yeah. Does it look like this, or did I get way off? Okay, good.
So is it the correct answer?
This is the correct answer, because this is the more stable carbocation. Here, it's a tertiary versus a tertiary, but this one has less ring strain. Yeah.
So like how many percent would we be expecting?
Yes, but the reason why I'm doing these here is because it would be hard for you to think of on your own, and I want you to see it. And then, now that you've seen it and you know it's an option, then you can be asked hard rearrangement things. But let's do a similar one here. We have a secondary carbocation, it's next to a tertiary carbon, but it's also next to a ring. So what do you think is going to happen? A ring expansion, yeah. So, we just draw the bond over. We now make a 5-membered ring. If I do my little numbering. 1, 2, 3, 4, 5. Who has a dangly bit? 1 has a methyl. And then who has the positive charge? 2. So here we did 1, 2 alkyl. But then what type of carbocation is this now? 2 prime. And it's adjacent to what type of carbon? Tertiary. So what could we do? Well, if we did a methyl shift, then we would just wind up with, like, here's the methyl, and then we would have a positive charge over here. So it would still be secondary. A hydride shift. So when we move the hydride instead of the methyl, that is going to let us create that tertiary carbocation at the top. So this is one where we had 2 shifts going on. Cool. Challenge problem 6 has an intermediate that looks like this, which is kind of weird. And one thing I'm just going to show you, I'm going to show you this, I wouldn't expect you to predict this, is this fused, like, bridged ring here can do a rearrangement that would be something like this, where this sigma bond moves up. The only way that you would know to do that is because in the product of the question, you see that there is a 5-membered ring and a 6-membered ring. And here, just so that you can kind of see it, I'll highlight. So this is a 6-membered ring, right here. Does that look like a closed ring to everyone? Okay. And then here, this is a 6-membered ring. And in the product, it has a 6-membered ring and a 5-membered ring. So that's how we would know to do this. The reason I'm going to do this is to do our numbering to try to draw what the next thing is, because that's going to be the tricky part. So let's do 1, 2, 3, 4, 5, 6. And so we know that that ring, did we break any of the bonds in this 6-membered ring? No, we just moved this thing on the outside. So we know that our next step, we are going to have a 6-membered ring. And maybe I'll do 1, 2, 3, 4, 5, 6. And then we need to do the rest of it. So I'm going to number going down 7, 8, 9. So the bond that we changed in our rearrangement was initially 2 was bonded to 9, and now we're going to make 1 bonded to 9. So over here, I have my first 6 carbons. Where should I place carbon 7? Connected to 6, good. Bless you. And then 7 would be connected to 8, which would be connected to 9, which would be connected to 1. So 7, 8, 9, 1. So now we have this 6-membered and 5-membered ring fused together. Again, the why would be because we would have given you a product that would show this type of ring structure. And the thing I'm just wanting you to see and get practice with is this drawing of it. Now, where's the carbocation? Who did we rob? 2, yeah. And what type of carbocation is it now? Secondary? Could we make a more stable one? Yeah, we could. It's next to a tertiary carbon, right? So secondary next to a tertiary carbon implies what kind of shift should we do? Hydride. Y'all are catching on. I see you. So now I'm going to draw this kind of cleaner. I would have this here. And so this would be 1, 6, 5, 4, 52, 7, 8, 9. And then you would go on and do the reaction. And like this will do an SN1 and an E1, you'll get products. But just showing you weird things. Yeah?
Just to clarify, on carbon 1, before any shift, does that have, the carbon cation, does that have 2 hydrogens or 1 hydrogen?
1 hydrogen. Mm-hmm. Yep. So here, as it initially exists, there's 1 hydrogen, right? And then it has 3 bonds to carbons. Over here, it has the hydrogen, but only 2 bonds to carbons, because our rearrangement robbed it of this bond. Formal charge, the valence is 4 minus 3 bonds is positive 1 charge.
Our overall charge in this class is 1.
Yeah, you'll never see a 2. Last thing, and just trying to wrap it up because carbocations want to run away and be like a huge section. Challenge problem 3 is weird. And it has a very important sentence in the instructions that if you don't read the sentence, you won't get the question right. So I'm going to read the sentence loud. This carbocationic shift is observed to occur simultaneously with the departure of the leaving group. Great. So basically what that means is instead of a leaving group leaving, forming a carbocation, then a rearrangement, it's saying the rearrangement and the leaving group leaving happen at the same time. So what has left in starting material versus product? This N2 thing. So we know that we are going to have an arrow that goes like this, and that's going to leave somehow. But we do some sort of rearrangement. So where, like maybe can we start to map some things onto each other? So like I see this carbonyl carbon. Do you feel like that's probably this green one that I highlighted over here that's connected to the OH? Yeah, that seems likely because there's already a CO bond. Has anything moved? Do you notice anything that has not there or has moved to a different location? The methyl, yeah. So where did it move? It moved down here. Okay. So just based on our arrow, we know that it's going to be this kind of methyl shift and then the leaving group leaves. Now to kind of explain why this would happen as one step and why this would not do a carbocation, I'm going to try to briefly show you this like MO argument. So we are breaking the CN bond there. So that means we're putting electrons where? In what orbital? The antibond. So let's draw that antibonding orbital. So that's the sigma star CN. And then the orbital that's our donor in this case is going to be this sigma CC. What do you notice geometrically about the relationship between these two? How are they connected to each other? How do they look relative to each other? They're parallel. So this is exactly like what we were doing with that like anti-periplanar orientation, where we had this kind of lining up of the orbitals exactly right so that the electrons could just scooch over. Again, you're going to see that type of stereochemistry argument come up a lot in Chem 27, so I just want to like flag it when we see it now. So, in drawing the next step, we have our rings. Bum, bum, bum. Oh, that's not right. Here we have OH still. And when this moves initially, like very initially, that CH3 is going to be up like this. But remember, we still have a hydrogen on that carbon. So it's going to look like this. Does that look right for this chair structure? No. Is this an axial up carbon? No. And so right when it reacts, it's going to look like this for a minute. But then it's going to just rotate down to its normal chair position. And so when it rotates down, that CH3, which was kind of axial up for a minute, is now equatorial up, and the hydrogen has rotated to the down position. That's kind of tricky, like y'all haven't seen something like that before. But does it at least make sense that this thing was up, and so it should be in the up position once it shifts? Because otherwise she's going to have to do a loop-de-loop and go under and roller coaster, barrel roll, what have you. So, I was going to ask, this carbon, well, I've given it away. Where's the positive charge on that carbon? So, what's the hybridization of that? sp2, because we have an empty p orbital. So that means that this is planar. This is all flat. That's why it's neither axial nor equatorial. I did not just draw an ambiguous bond. That's how it looks. Okay, is this a stable carbocation? Ish. Does anyone think it's a very stable carbocation? I'm looking for a word. Can someone say the word? Resonance. It's always the word. We are next to something with a lone pair. And so we have a resonance structure. And at this point, I'm going to write it in the form of the perspective drawing. So our methyl was up, so it's on a wedge. And then here, our resonance structure has a full octet. And so ding dong, like we're here. So our last step is we just have to deprotonate. Yeah. So the hard part here is clocking that this has resonance. Like, the thing is, this structure has resonance, and so it's how do we get to where we're seeing that? And my thing is, it's part of the general check whenever you have a carbocation. You should look at the neighbors, see if it can get something more stable, or if there's resonance. And so that's going to be kind of the checks and assurances measure. It's not even that. It is this lone pair is in a p orbital because it's next to an empty p orbital, and so there is resonance. It's not that we want it. It's just we are showing the resonance of this bond.
So the first one is correct, but it's just there's another resonance.
Yeah, like these are resonance structures talking about the same molecule, and this is just the more stable resonance structure because you have complete octets. Yeah.
Would it be incorrect to just do right there or just move the hydrogen?
So we would have to count off like a point or two, and it's because in organic mechanisms, you always need to show the most stable resonance structure, because that's going to give you the best idea of what's actually occurring with the electrons on the molecule. So you always have to show the most stable resonance structure. Work. Let's talk about making alcohols leave. So our problem is alcohols are not very good leaving groups, and Tim went into a little bit of why for that. And I'm going to first talk you through a kind of half-baked solution. So in like layperson terms, you take your alcohol and you dump it in a vat of acid. Let's see what happens. So our strong acids, concentrated HBr, HI. If you did it with a tertiary alcohol, you would protonate this, and then you could form a stable carbocation. Leaving group would leave. So then you have a tertiary carbocation, fairly stable. The halogen, either Br or I, would come in and attack. You would have an alkyl halide. The OH has left. Okay, so this is an SN1 strategy. The other one is if we have a primary alcohol, we would protonate it, make it OH2+, and then the halogen can go and do a backside attack as an SN2 reaction. So those are fine. Those work. The alcohol leaves. Can someone, without looking at the page, give me a reason of why this is not the best strategy? Let's assume we're rich. We are at Harvard University, and they will buy us all the acid we want.
I'm just going to use the whole program. This is just one step.
Well, so the first step, the protonation, is not the SN1 or SN2 step. Like we would describe a step as being SN1 or SN2. And here, it's these two steps are the SN1 steps. Yeah. But it's just because we're in strong acid, we'll protonate an alcohol. So I mentioned tertiary and primary. What about secondary? Would secondary be good at doing SN1? No, it would be fair. Would secondary be good at doing SN2? No, it would be fair. So one, this doesn't really work for secondary alcohols, so that's one downfall. The other thing is like, what if you had an alcohol that you want to make leave on a complicated molecule that had like a nitrile and a carboxylic acid and all these other functional groups that we don't want to react? If you put things in acid, acid is going to modify all of the functional groups that it can. And so, because we typically don't want to react with all these other things, like we don't want to use these harsh acidic conditions, that's why this is not the best solution. So, when you think about like making alcohols leave, this should not be the first thing that comes to mind. This is something that you can use, you will see it on the problem sets, but this should not be the first strategy. The first thing that should come to mind is these family of reactions that are very specific. So, we have three variations of them. We can either turn an OH into a tosylate, OTS, a chlorine, or a bromine. These, we do teach you the mechanisms, and they're fairly short mechanisms. They're mostly like SN2 kind of things. But the big thing to pay attention to here is the line reactions and the stereochemistry. So, for example, for this tosylation reaction, your OH here is going to go and attack the sulfur and kick off the chlorine. And then, when you do that, you will have this structure here with a plus that you deprotonate, and you get to the final structure. This is an okay abbreviation for the tosyl group, like it's this long, big thing, but you don't need to write all that. Big thing, did we attack this carbon and do an SN2 inversion? No, at no point in the mechanism did we attack that carbon and do an SN2 inversion. And so we would say that we've retained our stereocenter. We have retention there, wedge to wedge. Whereas in both of these reactions, which I'm not going to get into the details a bunch, but there is a step where either chlorine or bromine is going to do a backside attack, SN2, on that carbon. And so what we get is either a Cl or a Br here that's now in a dash instead of a wedge. So these two versions would do inversion. And again, that's why we are giving you options to retain or invert. One brief note I want to make here is this step where the chlorine attacks, you push up and kick off a Cl. This produces SO2, which is a gas. And that is super favorable. That is like the driving force of many reactions. And the reason why connects to some Gen Chem stuff. So do y'all remember Le Chatelier's principle? So the idea of, like, let's say you have reaction A plus B goes to C plus D. Let's say I decreased my concentration of D. Would that shift this reaction to the left or the right? The right, because it's trying to reach equilibrium. So when you make a gas, like SO2 here, it is going to bubble out of the solution, and so she is gone, and it's like we're getting rid of it as a product, and it will keep driving the reaction forward. Super, super important strategy that you'll see coming up later, and so I just, again, want to kind of clock it. So, for a little practice here, I made a variant of page 14 in Skill Builders that I think I made it a little bit harder. But what I want you to do is take a couple minutes and try to predict what the products are going to be for this first one. And then for these, think back to what the nucleophile you needed to have before, and then what the stereochemistry would be. Stereochemistry is going to be your biggest thing to pay attention to here. So take a couple minutes, talk with each other. No, you'll have to figure out what it is. Given, yeah, it's like Sudoku or something. Yeah, the first step is the OH attacking the sulfur, kicking off the Cl, and then you get to this intermediate that I've drawn. Or I show a step. NaSH. Ash. Well, I mean, it's SH minus as a nucleophile, covered up with a counterion. Yeah, or KSH. Yeah. Okay, like 30 more seconds. So, SOCl2, is that inversion or retention? Do we do an SN2 step? Inversion, so we have an SN2. So should our Cl be on a dash or a wedge? Dash. Okay, then KCN, is that SN2? Because it's going to be fair for E2, it's the medium base strength, and it's a great nucleophile. It's also fair for SN2, so SN2 predominates. So we add in a CN substitution, and should it be on a wedge or a dash? a wedge because we're doing another SN2. Okay, in our product for the next one, we have N3. So what should we write as our nucleophile? NaN3 or KN3. So you're just going to need that N3 minus and then something to cover up the charge. And then is that going to be an SN2 attack? Probably, yeah. I do write SN2 product for this column. So that gives it a little hint. So SN2. So we need to have some sort of leaving group here before. And does it need to be on a wedge or a dash? A dash, okay. So if we need to go from an OH to a leaving group on a dash, which of the options do we have available to us? Yeah, we could go to chlorine or bromine because those are the two that invert here. So I'm going to do PBr3 just to mix it up. Yeah, just one of them you would put a chlorine on a dash, one you would put bromine on a dash, but both are fine. Sometimes you might want a chlorine, sometimes you might want a bromine, but if you're about to just kick it off, no, there's no difference. Okay, the bottom one, SH. Well, your nucleophile would be SH minus, so we want NaSH as our reagent. Okay, we've done SN2, so again, we know that this has to be dash. And here we started dash, so if we go dash to dash, which leaving group are we making? Tosyl. So we use TSCl and pyridine, and we would have OTS. Cool. So here, if we kind of back up, we wanted to replace an alcohol here with some nucleophile. And overall, we can think about this whole process as either being retaining or inverting. So here we went from an alcohol to a cyanide, and we retained stereochemistry, but we did that retention through two inversions. And so there's this kind of idea that double inversion back, is the same as retention, visually. And that's a big kind of thing to keep in mind. Whereas these, where you're going from a dash to a wedge overall, that means we only had one SN2 step. So, what's that I hear? A wild synthesis strategy! Oh my gosh! So, if we started an alcohol and we wanted to make that cyanide, we could do it with either the retained stereochemistry here that has two inversions, or an inverted stereochemistry that only has one SN2. And our choice of how we would make it into a leaving group is going to control that stereochemistry. Was that too much? Was that a little extra? That was a little extra. No, because I wanted to reveal. Yeah, I even put like a white box in front of it. It was a whole thing. So, cool. Does this idea make sense though? That this stereochemistry is going to be something we want to control? Yeah.
If we had a problem like that where there was a double SN2, would it be better to do like a TSCL?
So that would make it into OTS, like if we did that.
Oh, yeah.
And it's specifically wanting to get to a CN. And so it really has to do with the idea that like overall, we're kind of wanting to do it like a substitution with an OH, but no matter what we do, we have to go through a leaving group because OH is not a good leaving group on its own. And so it's balancing the stereochemistry of those steps. Yeah. Now I'm going to do a quick non sequitur, and it's challenge problem 4, and it's really easy, but I think it just trips students up. So you're faced with an alcohol and this oxygen phosphorus thing that kind of reacts like PBr3, kind of. And we have these products. We have an alkene here, so what type of reaction had to have occurred? An elimination of some sort, like E1 or E2. And then, what do you see is different between the phosphorus compound and the reagent and the product? Yeah, it has an oxygen, and then what else? Well, this isn't a carbon, so, you know. Yeah. But, big thing, we have 3 chlorines initially, and now we only have 2. So, the first step at the PBR was the OH comes in, attacks phosphorus, kicks off a bromine. So, what do you think would be an analogous step to do here? Attack the phosphorus, kick off chlorine. And hey, we know we have to kick off chlorine either way. Okay. Well then, now we have this kind of charge thing, and we can probably just like neutralize it and see where we go. Because if we look at this other O on our product, it's an O minus rather than an OH. So that's kind of a tip off that we would have to deprotonate at some point. So let's take our pyridine in the solution and just deprotonate real quick. So if we go back to our PBr3 mechanism, this is the point where the Br would come back from behind and do an SN2. Why is that not a good candidate right here? Say it. What? Sure. But also, like, we already know secondary is not good for SN2, right? And a secondary ring is even more sterically strained. And so it's just going to be hard to do an SN2. The other reason is we know that we're going to do some sort of E reaction, E2 or something like that. So maybe let's try for an E2 and see what that would look like. So what would we do here if we assume that this is a good leaving group, which we can make that assumption because it left. Like we see it off, this exact thing. So how should we do the E2? I heard like 3 people whisper beta hydrogen. Just really beta hydrogen. So we have to deprotonate a beta hydrogen. Let's do it. We can take our pyridine again. Fold in, kick off our leaving group. Here we have 2 hydrogens on this molecule, and so we can assume one of them is probably going to be antiperiplanar without doing full chair things. So maybe, but like it's the thing of, let's say, like your solvent is pyridine, so you're just going to have a ton of pyridine. Whereas the chlorine, you've kicked off 1 at this point. And so it could, but it doesn't totally matter. You could just say sol. Yeah. The other side's going to form the exact same product. Yeah. Cool. So again, just because it's kind of connected to that phosphorus, I wanted to flag it here. And then this is a challenge problem that is not too bad.
Would it be wrong to do the deprotonation first and then it's like
That would be fine.
And then deprotonate the
At the end, yeah, that's fine. Yeah. It's a thing where here I saw the O was deprotonated, and so I thought it would probably just do that in the middle and make a more stable intermediate. But like that type of protonation state thing is not something we would really count off for. Because you would really have to know like pKa values to answer definitively, and we don't know the pKa. I don't. Cool. Are y'all okay on alcohols leaving? Can we leave this topic just like the alcohols? Okay, let's see what this one is. Drama. We come to ethers, which actually are the most boring of all the functional groups. I'm going to start off by teaching you a tool that I like to use on ethers that is truly a me thing. This is not like formal nomenclature, but for me, it is really helpful to like classify ethers by the types of carbons on either side of it. So like, for example, this carbon on the left is a primary carbon, and the carbon on the right is a secondary carbon. So I would call this a 1' plus 2' ether. Then the next one, what's on the left? Tertiary, so this would be a 3' plus 2' ether. And then real quick, do the other ones. So, again, it's just a way for us to kind of recognize that not all ethers are equal. And this is going to be important for us because, again, we're going to have this SN1, SN2 dichotomy. And so it's going to be helpful to kind of classify these. So, how to build an ether, which I only hear in my head as like, how to build an ether, dun, dun, dun. The How to Save a Life. But, wow. Heard. The one reaction that you should know that like is probably one of the most important reactions of this lecture is the Williamson ether synthesis. It's a two-step process for making ethers, and it should be your go-to first strategy for making any ether. So let's look at it. The Williamson ether synthesis is you start off with any alcohol, and here I'm using this notation any prime. Again, this is a me thing of like this could be like this, like primary, it could be secondary, or it could be tertiary. It could be any prime. And here the one just indicates like this is an R that's different from this R. It doesn't mean that there are two of them. So what would happen is you would add NaH, specifically NaH as the base, because NaOH has weird things with like equilibrium reaction. So then that would form this alkoxide. And then the second step, you add a primary alkyl halide. So here, if you have an alkoxide and a primary alkyl halide, you'll do a backside attack. Bada bing, bada bang, we have an ether. And I've tried to do some highlighting to show you where each of the atoms came from. So this strategy can make any ethers where one side of it is 1 prime. So like, for example, these 4 ethers at the top. Which of these could we have made with Williamson ether? 1 and 3, exactly. Because one side of it's primary, so it could have come from this alkyl halide and this alcohol. Same over here. So, making a 1 prime plus any prime ether, Williamson ether. That's your go-to. It's the main one you're going to use for synthesis Bach problems. The other option is doing an SN1 route. And so to do an SN1, we would want our alcohol to be tertiary. So for this, we would just use alcohol and an acid as our other reactant. We would protonate this tertiary alcohol, leaving group leaves, we get a carbocation, and then the other alcohol would attack. So it's just doing kind of an SN1 reaction where your first step is you protonate the OH. So this can make any ethers that look like they have a tertiary on one side and then anything else on the other side. So of the top 4, 1, 2, 3, 4, which of these could we have made via SN1? 2 and 3, because these are the ones that have tertiary on one side.
How did you protonate again?
So I protonated, we have H+, so OH2+. Then this leaving group leaves, and I have the carbocation. Then this attacks, and I have the structure that looks like this, but now it's this. And then there's a final like deprotonation step. Yeah. But see, the mechanism for all of these are mechanisms that you could have easily seen in lecture 6, but now that we're talking about it with the functional group, it's this own thing. You can do things like intramolecular reactions and form an intramolecular ether this way if they're on the same molecule. And then I'll also flag that you'll learn 2 other ways to make ethers coming up. So just keep an eye out. We have 2 strategies for destroying an ether, which are also SN1 or SN2. I don't want to talk about it because it's kind of boring. It's basically the same thing, so I'll let you just use this as reference. Big idea, you're using concentrated acids to do this. And it's because ethers are not very reactive. Like, they're pretty darn inert. And so in order to break up an ether, you have to use strong reaction conditions.
What is the
Heat. Yeah, no. This means heat. It was in a infographic that was very, very small on section 3. Oh, work. Okay, the warning here is we said that there was an easy way Williamson ether to make these. We said that there was an easy way with this tertiary side one to make this. When we have secondary or secondary ethers, it's tricky. Why is it tricky? yeah, it's going to be fair for both SN2 and SN1, and so it's going to be hard to kind of control that reaction. There's going to be a skill builder that I think like gets you to explore that a little bit, but that's just something to watch out for. 90% of the time, if we're asking you to build an ether, it will be this or one of the ones that you'll learn in lecture 8. Epoxides. Moving on. One of my favorite functional groups. I just think that she's kind of cool. She's very dramatic. I'm ready to explode. Also, epoxide, her government name is Oxyrain, which is just a kind of fun thing. Like that is what you would call this functional group in IUPAC nomenclature. The other really fun name is the thioether. You would call mercapto. I'm just like, what? Who'd have thought? Yeah. You only know one way of making epoxides at this point. You will learn another way in lecture 8, and it's one of my favorite reactions, so keep an eye out for it. But we use this compound functional group called a halohydrogen. And it's halo because we have a halogen, and a hydrogen because we have an OH. And they are right next to each other. So you will fall into a trap if you looked at something like this, and you circled this and said alkyl halide alcohol. Here, because they are next to each other, they're going to interact how they react, and they're going to be able to do special things like this epoxide. So keep an eye out for her. The mechanism is we just add base. It deprotonates here, makes O-, and then the O- does an SN2 backside attack. Cool. So, with epoxides, here, with a symmetric epoxide, anytime we have a nucleophile, it could attack either side, but it doesn't matter because both sides are the same, right? But when we have an epoxide that's a little bit more complicated, something like this, here, if our nucleophile was going to attack this, we would want to control whether or not it attacked the top one or the bottom one. And so the way we differentiate the sides of an epoxide is by how substituted it is. So here, this top one is like a tertiary carbon, and the bottom one is a secondary carbon. So the top one is the more substituted side of the epoxide. The big idea here with epoxide opening is whether or not you're an acid or base, that will determine what side the nucleophile attacks on, the more substituted or less substituted side. So if you're an acid, you're going to attack the more substituted side. So for these reactions here, the nucleophile is in this dark red, and it added to the more substituted side of the epoxide. And then the OH that's on the other carbon, that is the O from the epoxide itself. The mechanism for it is if you're an acid, your first step is going to be you protonate this. And essentially the reason why the nucleophile attacks that more substituted side has to do with like partial positive charges here. And like this one is the one that is more stabilized by hyperconjugation. It's kind of a hand-wavy explanation, but like I think having some basis of like understanding why acid more substituted side is helpful. And you can do things like add an OR, and then you make an ether. We found one of our other ways of making an ether. Oh my gosh, so exciting. And it's specifically an ether with an alcohol next door. And then you could do it with H3O plus and then get this glycol or vicinaldiol. If you do it in base nucleophiles are just going to attack the less substituted side because it's faster. And so here, our nucleophiles for these reactions are in this kind of dark blue over here, and you see that they have added to the less substituted side. The last thing that I kind of want to touch on here, I know I'm going very fast, I'm not explaining all of these reactions because I mostly mean this to be an infographic for you to use later. The last thing to kind of touch on is the stereochemistry. So this epoxide, it is on a wedge, so it's kind of going up above the ring. And so if we visualize it, if we bust open the epoxide, the antibonding orbitals are going to be below the ring here. Does that first idea make sense of if our epoxide is above the ring, our bonds are up here, our antibonds are going to be below the ring. So what that means is when our nucleophile comes into attack, either side, whichever side it attacks, it's going to be coming from below the ring. which means our nucleophile is always going to be added on a dash. For here, this epoxide, where it's on a wedge. Yeah, it's kind of this interesting thing of like, yeah, it would make sense for this to be on a dash because it had to approach from below when it broke this bond. Yeah.
That's when the epoxide is
Wedge.
on top, wedge.
And if it was dash, then it had to approach.
on top.
Yes. So
And
the
can you
nucleophile.
have an epoxide on the same thing?
No.
You cannot have that.
Well, so if you were doing that, then you would have to have this. She hates existence. She wants to be 120 degrees, and you're making her 60 degrees. And so, yeah. Yeah.
If there was no method and it was just the laying of the epoxide on
Then,
it doesn't matter.
yeah, it doesn't matter. This is truly only for when it matters. In some cases, we'll give you it does matter, some it doesn't. But with the infographics, I tend to want to give you a hard example to show you the most complicated version of what you'd be expected to know. Yeah. So, if you had this epoxide. So, if you attack this side or this side, it's the same. Yeah. And it has to do with symmetry. But cool. I had a little practice, but the section 7 stuff takes longer than I want. Like I'm about 10 minutes over what I wanted. And so I'd like to just move on if that's okay. I know I did a very light touch of ethers and epoxides, but I really think that y'all will be fine using these kind of infographics to go back and study later, because most of this is SN1 and SN2 style reactions. Okay, let's see what this one is. Ooh, okay. So welcome to How to Study Reactions Part 2. Thanks for coming back. So, y'all have done the first exam. You've had to study some reactions. You are working through problem sets, and you're starting to kind of think towards studying for exam 2, which is in 13 days. The issue that we all face, sorry, that was a lot to drop. The issue is you need to be figuring out a way to study reactions that, one, is going to prepare you for how you're going to be tested on them, and 2, is time effective. And there are a lot of strategies that many of you have tried different things. I've seen people with like flashcards, I've seen like whiteboard folks, I've seen like lots of different strategies. I want to introduce a strategy that I really like, and we're going to try it out, and then I'll tell you why I like it. So I call it doing a die. I don't know, just a little bit morbid, but it stands for the Desert Island Exercise. And have you ever heard of like the phrase of like, I'm going to take this exam under like, or practice exam under desert island conditions? Well, essentially it means, imagine you're on a desert island, you only have your pencil in the exam. You have no other materials with you. You have no kind of crutches to use. Desert island. You do what you can. So here's the setup for it. On a blank page, either paper or tablet, write out the starting materials of the reaction that you want to study exactly as it appeared in lecture. So we're going to be doing it with the amine reaction from lecture 5 today. And this is exactly the lecture, like, reaction molecules that Serena used when she taught it to you. Then, put away all your notes. Close all the other tabs. Get out a timer, and we're actually all going to do this, so can everyone get out a timer on their phone? And we're not going to press start yet, but set a timer, or prepare a timer for 3 minutes. And for those that are using paper, go ahead and write out these molecules and this arrow down, because we are actually going to do this exercise for the next 3 minutes. If you're a tablet user, you can write on here, but just get the timer ready to go and kind of have this over here. And what you're going to try to do in these 3 minutes is you're going to try to first predict the product, and then second, write the full curved error mechanism. Yeah. So does everyone have this down? Because I'm about to move it off, and I'm going to do the exercise too. Yeah. The functional groups on there, yeah. The primary amine and the carbonyl. So, I'm going to count down. We're all going to start timers. It's going to be a 3, 2, 1, go situation. So, 3, 2, 1, go. Ah, I love that. So, how did you do? How did I do? Take a minute and check yourself.
And you just know you just think about solid, you don't know.
So, yeah, you're in an aqueous solution, so if you want to write H2O, you could use HOH, sure, or like H3O. But again, this is a version of writing it that would get full points, and so I would encourage you to like use whatever shortcuts that you can that are permissible. And so I think Sol is a really useful one. Similarly, like proton transfer. Like, you don't need to draw curved arrows in this step, you just have to draw proton transfer, and we will assume that you know how to do the protonation and deprotonation. So, other questions about steps on this one? Yeah.
I think this is really basic, but how do we know, like what version of the nitrogen should be?
The amine or enamine?
Yeah.
So, this exercise doesn't really address that question. That question it gets back to, like, if you use a primary amine, it forms an amine, and secondary forms an enamine. This is for if you know you are trying to work on getting the product and doing the mechanism for a specific reaction, that is what this scale is useful for. There are other ways where like knowing, like spotting that this is an amine reaction, that is a kind of different skill than what this is working on. But this, working on this way, will help you with that skill. Yeah.
And more like specific question, would it still work if you did the coordination for L before the protein transfer?
So you can. It's not my preference because when you do it that way, you don't form the hemiaminal. And the hemiaminal is the most stable intermediate structure, and so I think it's good form to show it. The protonation states here, I don't think we would come off on the exam for something like that, but again, it's my preference. Everyone has their preference. Yeah. So this, when you were doing the one that's exactly from the lecture notes, you have the answer key, which is the annotated lecture notes. You can go through and check it. And specifically, it's good for not only like diagnosing like what is wrong, but diagnosing what took you the most time. Like, did it take you 45 seconds just to write what the product should be? Like, were you having to think through mechanism things to get to the product? If so, that's going to be too long. Like, you want to get to where you could generate a product from a reaction that you know in about 10, 15 seconds. Just because you're going to have 3 pages of box problems, and each of those are going to have like 3 or 4 line reactions on it. And so if you're having to take more time than that, you just won't have enough time to finish the exam. And so it lets you kind of target how you're spending your time. The other thing that I really like about it, I'll get to all the things I like, is I like how confronting it is. Because I saw several people who at some point just stopped writing, which is fine, but like this is a concentrated way to feel that discomfort that can be very motivating of like, oh crap, I need to learn this. And also it gets you to ask the question, how do I know what the first step is? And like for me, that's going to be like, oh, okay, I need to add the nitrogen somehow. I need to get rid of this oxygen. So my first step is probably add the nitrogen. And like then you can kind of like talk yourself through it. And as you do this with more reactions, this process is going to be faster, getting really comfortable at it. Like my personal goal for the reactions for this class is to do this whole thing in like a minute, which I did for this. But it's a really great like self-assessment tool. And then once you do this once, I would stop at the 3 minutes, do a hard stop. Do not keep working on it. Grade yourself, get some feedback, try the exercise again until you're comfortable doing this. Then that's kind of the first stage, the basic reaction. Then you can kind of differentiate this and build on it. So try it now with a different amine or a different carbonyl. Try to draw things in weird ways to trip yourself up and to make sure that you could still apply this reaction in a lot of different settings. If you really want to challenge, try doing an intramolecular version where you put your amine and your ketone or aldehyde on the same molecule. Like there are ways that you can kind of step this up and make it harder based on what you need for your studying. And sometimes you need more of the basic examples. Sometimes the next example is you're going to have a methyl here instead of a phenyl group. Or you're going to have an ethyl and an ethyl. Like you're just changing the identities. That mostly is going to change what your product looks like, but the arrows will be the exact same. And really you're just going to kind of build up that speed and confidence with the arrow pushing so that it becomes not an issue on exams. Because you want to use your exam time thinking and brainstorming like which reaction should I be using. And if you're also having to pause and be like, how do I do this step? How do I do these arrow pushing? Then you just don't leave yourself enough time. Then you can do things like start with the product, do the reverse reaction, work on the disconnection and the mechanism. But just kind of zooming out why I like this, one, it's active learning the whole time. Like you are not wasting any time. It's not like something like flashcards or like rewriting your notes where that requires like a big time investment to make the material before you can even really use it to study. And then also when you're just like copying down things from lecture notes or putting them into a Quizlet form, that's not active recall. Like that is like passively rewriting information. So I like that it's like really kind of active learning the whole time, and it kind of confronts you with the amount of information you will have on hand at the exam, which is whatever's in your head. I also like the time constraint because it only makes you do this for 3 minutes, and so you can't kind of fixate or spiral on a reaction. It has this kind of built-in. I have to pause and take a step back and like self-assess and figure out what's going on. And then it's this like flexible tool that you can make as hard or as easy as you need. If you do one of these like die exercises on a reaction and it's really easy for you, you can do maybe one more and then just move on to a different reaction. You don't have to do this like a set number of times. But I really like it as a just tool for you to use, both to diagnose your own understanding and what you could do on an exam, and also as a tool to practice and learn the basics of the mechanism. Now, again, to what y'all were saying, this doesn't help you like target, spot a reaction in the wild. That I typically think of as like retrieving reactions, whereas this is kind of the encoding the reactions, like making sure that you have this information deep within you somewhere. And How to Study Reactions Part 3, we'll be talking about the retrieval. So, it's coming. Yeah.
How much reversing on the fair vision or I think you said it was less.
I mean, you're going to have, I think, 3 pages of box problems, 2 synthesis, 2 mechanisms, and then like 2 theory. Like that's kind of the breakdown of exam. Theory, like basicity kind of things, like you haven't gotten to it yet. A lot of it's lecture 9 for the theory questions, but we could ask you a thing about a carbocation rearrangement as part of a theory question, or we could ask you about SN1 versus SN2, like talking about carbocation stability, that kind of like theory.
But not like paragraphs.
No, never. I don't like great paragraphs.
Not like with the conceptual things or like.
No, I like giving y'all little bubbles that you can fill in a bubble, and I can say great, or I can say nope. Yeah. So that's How to Study Reactions 2. That leaves us 12 minutes, which is tight. And to be very honest, I will probably go 5 minutes over. But I would really like to talk about challenge problem 10 with y'all because it's the hardest synthesis you've seen, and it's a very different game from the synthesis that you've seen up until this point. And so I think it would be really good practice to work this together. Maybe. On to synthesis. So, here, challenge problem 10. What's the first thing that we should do when we start synthesis? Look at the functional groups. So, what functional groups do we have here? We have like arene and alcohol, good. So alcohol is the one that we know reactions for, but the phenyl group, that's going to be a nice kind of benchmark to be like, hey, we could probably spot that in the product pretty easily. Did we see the phenyl? No, I gave it away. Is the benzene ring somewhere in the product that you could spot? It's probably this phenyl, right? We just didn't write it all out. Okay, interesting. So what that means is the carbon that's right next to that benzene ring is probably this carbon on the double bond in the product. Do you buy that? Yeah. I think that that's a reasonable assumption that someone could make. So we've mapped this kind of orange star carbon. What functional group do we have in the other starting material? It's like I'm in a forest and I had a hole and I covered it with leaves and you all fell into the drum. I've caught 20 Oakham students. What is this functional group? A halohydrin. And again, it's because you have these right next door to each other, so they are going to affect how they react. They're going to react as a different kind of functional group. Well, halohydrin, you only know one reaction, right? What can a halohydrin form? We can form an epoxide. So, we can just go ahead and draw that. Like, we know that that's probably going to be what we form. I also spot another kind of structural feature here. Like, what is something structurally that stands out about this molecule? It has to do with this carbon, yeah? You have 2 methyls on the same carbon. And like, y'all don't know how to like remove a ton of methyls in like a synthesis. So maybe we can try to find a carbon in the product that has 2 methyls. So do you buy that those are probably the same? Okay. Well, then let's go one out from that, and let's label this other carbon green star. So, do you think it's probably safe to assume that green star is this point in the product, the one that's one further out? Okay. So we've kind of mapped our starting materials onto the products as we were doing functional groups. Let's look at the functional groups of the product. What do we have? Yeah, I heard them all muttered at the same time. So someone said ether. So yes, we have an ether over here, which brainstorming wise, we can think Williamson ether. And what was our other way of making ethers? Yes. What was the third way that was like the plot twist later? Epoxide. So we can make ethers from epoxide. And then someone else said alkene here. So alkene, what are our ways of making alkenes that we know? So we could do E1, E2. So why don't we do our kind of retrosynthesis? What would it look like right before we form an E1, E2? Because either forming the ether or forming the alkene is probably our last step in our molecule, right? Like those are the functional groups that we have. So one of those are probably the last things. So we know that we need some sort of leaving group, right? Well, I could place my leaving group here on the left side of where that double bond was. Or I could place that leaving group on the right side of where the double bond was. So we have kind of two options. And this gives us kind of a benchmark for where we will need to put some molecules and try to get to something that looks like this. Because once we get to something that looks like one of these, then we can make our alkene here. So at this point, I'm going to keep my stars because I think that that's going to be helpful for just kind of tracing some through lines here. And here. And I know also that a big goal of this reaction is going to be bringing these two molecules together with the green star and the orange star. So we are going to have to at some point make a bond here. And then one thing to kind of keep in mind with that is one of these are going to have to be a nucleophile and one's going to have to be an electrophile. And so one thing to kind of think about is which one's going to be which. Okay. Well, we've done some brainstorming with the products. Why don't we do some brainstorming with the reactants? So alcohol. Can someone tell me a family of reactions that we could do that starts with an alcohol? I really need more volume. To form what? Can you tell me a functional group that it would make? Because like alcohols on their own are not the best nucleophiles, but yeah. Sure, redox, that's one family. So the functional groups that we could make are aldehyde or carboxylic acid. And Erica, I'm not saying you're wrong, but just tell me the functional groups associated. What other kind of families and functional groups could we do? What was a section today that we talked about that started with alcohols? We could make it into some leaving group. So we could make it a chlorine or a bromine or a tosyl. Okay. Other things with alcohols. I mean, we have a hodgepodge. We could do ethers. We could do acetal. I mean, we could even make it to an ester. Like, there are other things that we could do, but this is kind of our main brainstorming. Okay. And then if we're thinking about like trying to make one of these molecules a nucleophile, one an electrophile, and we're pretty sure that this thing is going to be an epoxide, is the epoxide going to be the nucleophile or the electrophile? It's the electrophile. It wants to explode. Nucleophiles are going to come along and attack at one side. So we have an electrophile over here. So we need to figure out how to make this into a nucleophile somehow. And the other thing kind of I'm going to notice about that green star and orange star together is it is a carbon-carbon bond that we have to form. We're forming a carbon-carbon single bond at some point. And there are only a few reactions that we've learned that form carbon-carbon single bonds. And so can you think of a way of forming carbon-carbon single bonds using some sort of nucleophile? Like what's a nucleophile that can make a carbon-carbon bond? Grignard. So, like, I mean, if we think about it just abstractly here, RMGBr, that would create a new bond between our R, or like alkyl group, and another carbon here. So that's a route. And the other one that we did was lithium. So, okay, those are carbon nucleophiles. How can we turn this carbon that's on an alcohol into like a Grignard or like a carbon nucleophile? That's not any of the things that we have right here. But if it's a carbonyl, that's going to be an electrophile, and we already said that this is the electrophile. Ooh, okay. So basically we said, hey, our brainstorm initially, the things that we could turn the alcohol into directly, is not going to make a nucleophile. So what if we try doing to a bromine and then to a Grignard? We're ready to try an attempt. Yeah. So potentially, but the thing is, again, that would be a carbocation. Carbocations do a lot of things. Here it would be a carbocation stabilized by resonance. My big thing is just like, what would the nucleophile be? Because when you make it a carbocation, this would be an electrophile still. And we want to make this carbon into a nucleophile because we know this thing's an electrophile. So we could do it, but I don't know that it's going to be the most relevant for right here. And again, we might have to regroup, and we'll see. But let's try an attempt at this and kind of piece together these ideas that we have and see what happens. So I'll start off with making the epoxide. What reagent should I use? NaOH, it's on the previous page. Okay, we've made our electrophile. Then we have our alcohol. And my strategy is I want to turn it into a bromine. And then I want to turn it into a Grignard, MgBr. So Grignard reagents we know are magnesium and Et2O. What reagents do we need to turn an alcohol into a bromine? PBr3. And I know that not everyone has that just like on hand mentally right now, but do you at least know, okay, if I had to make it into a bromine, do I know where to look in lecture or section notes where I could find that reagent? That's where you should be right now. After you study all the reactions, then you're going to want to build speed of being able to kind of recall that. And again, we'll talk about study strategies for that next week. Okay, so now we've made our nucleophile electrophile. So what I'm going to do is I'm going to say, hey, let's take these two. Step one, we are going to combine in diethyl ether. And 2, we'll do an H+ workup. Now, question, is a Grignard acid or base? Base. So, if it's base and we're doing an epoxide, are we going to attack the more or less substituted side? Less. Base is always less. So, we're going to add it here. And, whew, thank goodness, that's the thing that we wanted. Like, we were just kind of going along and we didn't really check that. But we wanted this orange to attack the green, and that is the less substituted side. We're in base, so we should be okay. So we have an OH here that's from the epoxide. Then we have our orange star, and then we have our green star. So we've connected it, right? We've made that double bond. And you know, we could probably turn this into an ether. But what do you notice about these two? What? We want to make a double bond there, right? And we wanted to have a leaving group of one of those positions. But these are now alkanes. Like this is boring. And so could we form a double bond from here? No. So, what's the like funeral march? The brum brum brum. The taps, I think. Brum 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 brum. Laying to rest the synthetic idea. Brum 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 brum. So we had to do all this to know that this wasn't the option. And we wouldn't have known that sooner. And this is the thing, when you are working on a synthesis that's 10 or 12 steps and is this level of difficulty, you will probably have to go down a wrong path before you find the right one. So let's back up, and we're gonna fix it here in the next like 3 or 4 minutes. But essentially, we need to get another functional group present so that we can do this like leaving group elimination thing. And the thing that I'm going to kind of tell you as the insight from having done some synthesis, when you have two functional groups right next to each other, that is a tip-off. And particularly, two functional groups right next to each other is a tip-off for epoxides. Because anytime you react with an epoxide, you are going to be reacting with two carbons that are right next to each other. And typically one of them is going to be an OH and the other one's going to be something else. And that's a thing that's like hard to see and is a new strategy that I'm pointing out to you. So we need to introduce another functional group, and we need to do something with our epoxide before we do this kind of combination. So what are some ideas with something that we could do with this epoxide that would be broadly like working towards what we want? Like we know that this is like this part of the molecule. So what's something that we could do to it? And right now we're not focused on combining with this orange star. What remaining goal do we have on this part of the molecule that we haven't done? Yeah, making this little ether over here. So, what reaction could we do? Maybe I'll do some purple, where we add that ether on the left side here. So, first of all, if we are adding something over here, are we adding it to the more or less substituted side? More. So we need to do it in acid or base? Acid. So we'll need H+, and we're wanting to add OET as our ether that's formed, and so we use the alcohol HOET. So let's just see what happens from here. We don't know that this is the right answer, but it is something that's kind of working towards something that we see in the product. So we have OET, and then on the other carbon, the one that we've kind of called the green star going on, that has an OH, and that was the oxygen that was in the epoxide here. Okay. Well, now at least we have a situation where we have two functional groups next to each other, whereas before we only had one. Okay. We still need to combine these, don't we? So we still need to create this orange star, green star bond, and we've made a nucleophile here. So is there a way that we can make this green star into an electrophile? More, what? So you could make it into a leaving group that would do like an SN2, but y'all haven't really seen Grignards do an SN2. Sergio. You said make this into a carbonyl? Yeah, I mean, that's the first thing that y'all learned. Grignard's attacking a carbonyl. So, if we do that, we'd have OET here. And let's make an aldehyde. So what reagent should we use to oxidize? Chromium, CrO3. And if we stop at an aldehyde, should we use pyridine or H2O? Pyridine. Okay. So hey, now we're back at, we have a green star electrophile. We have these two functional groups now. And we have our orange star nucleophile. This seems promising. Let's do these together. So, step 1, combine in ET2O. And step 2, H plus workup. I promise we're very close to being done. So, over here, now the only difference is on our green star carbon, what should we have after we've attacked that carbonyl? Say a charge on what? Like a negative or a positive? So our Grignard is attacking the carbonyl. So we still have an oxygen on there. And so we'll neutralize it and we'll have an OH. So now we have something that looks really close to this. We have an OH here. We need to make a double bond. Are there any reactions that we know directly that could do an elimination from an OH? Say again? With what acid? You conk it. Concentrated H2SO4. So we could, if you wanted to, we could do like PBr3, make this a bromine, and then do an E2 elimination. That works. But we have an alcohol, so why not just do concentrated H2SO4, which will do an E1 reaction, and we're at our product. Woof. This is a different game. And like, again, this is why I wanted to talk through this with y'all, because we had to do so much planning when we are doing a 10 to 12 step synthesis. We are using reactions from every lecture that we've learned so far. It is something where you need to be comfortable both with thinking on paper with these ideas and brainstorming, and also with that recall of reagents and predicting products. And so those are going to be the things that you are going to be practicing as you study, of like, how do I just spot, oh, okay, what reagents do I need to go from an halohydrin to an epoxide, something like that. But I know this was a lot. Thank you for coming. I hope this was helpful. There are paper copies of the extra challenge problems up here. Remember the stuff that's due tonight. I'll be around up here to answer questions, but thank you. Thank you for letting me go over 10 minutes. My God.